So thank you for the introduction, and I'd like to thank the organizers for this opportunity to this conference and to talk in this conference. So I'm going to talk about the geometry of weighted Finsler spacetimes, and this includes some joint work. So this ends joint work in progress with Mathias, and also some other joint work with Yufeng Lu. He was my PhD student now in Hong Kong, and also Ettore Minguzzi. Okay, so let me start. So this is the plan and aim of my talk. So we developed geometry of weighted Finsler spacetime. And my viewpoint of this project is Lorentzian analog to Finsler geometry. So my background is really positive definite. So I did Riemannian geometry and Finsler geometry, and I did some work about weighted Ricci curvature, also called Bakliami Ricci curvature in the Finsler setting. And so recently, the Ricci curvature business is very active in the Lorentzian case. So it's natural to expect some Lorentzian analog to this Finsler geometry. And for some other people in this room, it can be also considered as Finsler analog to Lorentzian geometry, but to me, it's really the first viewpoint. And this is a plan. So I first review Finsler geometry. Yeah, so it's already explained it in the previous talk, but I will repeat some part. And especially I explain how it's a Ricci curvature, theory of Ricci curvature in the Finsler setting. And then I turn to the Lorentzian case. So I explain what can be done in the Lorentz-Finsler setting. And finally, I think I will very briefly explain about the Tamara curvature dimensional condition. So yesterday there are already many talks about Tamara curvature dimensional condition. So I just explained in the framework of weighted Finsler space times, we can also show the Tamara curvature dimensional condition from the appropriate Ricci curvature plan. Okay, so this is the plan. So as I said, I start from a positive definite case. So it is really positive definite theory. And in this talk, I consider only very smooth. So in this sense, my talk is very regular instead of non-regular theory. So I consider only any dimensional connected and smooth manifold. And then the Finsler structure, so it is already explained in the previous talk, it is like this. So we consider a non-negative function on the tangent bundle, and it is smooth, but only expect the zero section. As I explained in the previous talk, if it's smooth at the zero section, it's necessarily Riemannian structure. So we don't have the smoothness at the zero section. And then about the homogeneity, we assume only the positive homogeneity. So the f of cv coincides with c times f of v for any tangent vector v and only positive c. Okay. And then about the convexity, we assume the so-called strong convexity. This means that the Hessian of the square of this Finsler structure has positive definite, is positive definite. This is a strong convexity. And let me draw a picture of unit sphere in this structure. So when we consider in the tangent space, and we draw a picture of the unit sphere of this Finsler structure, and this is strongly convex, and of course includes the origin, but it's not symmetric, so it may be something like this. But it is smooth enough and of course convex, so it does not include the flat region, and it does not include any corner because of the smoothness. But it's not necessarily centrally symmetric. So this is a unit sphere in the circuits. And so, as I said, we have the non-reversibility. And actually, I think this is one of the most important features of Finsler geometry. So we can naturally include this setting in the context of Finsler manifold. And so, yeah, so by using this Hessian of the Finsler structure, we can consider a Riemannian structure on the tangent space. Yeah. Yeah, so if we fix some direction B, then so this Gij is a Hessian, so it's a second order approximation of this Finsler structure. Maybe like, or it's not really symmetrical, but so this is units here for this GB. So this is a second order approximation of the Finsler structure. And this is Riemannian structure, and this is actually very useful to study, especially the curvature of the Finsler case. So this is the definition of GB. And actually, instead of giving precise definition of the Finsler curvature, we can, in a sense, characterize Finsler curvature by using this Riemannian structure, GB, even like this. So this is a very useful viewpoint, so let me explain. So we start from some non-zero tangent vector B, and we extend it to a smooth vector field in such a way that every integral curve is geometric. So it's always possible. So we start from some vector at point X, then we extend it to a vector field on a small neighborhood in such a way that every integral curve is geometric. And by using this construction, we have a Riemannian structure G associated with GB associated with this vector field B on the neighborhood. And it turns out that the Finsler Ricci curvature, this is defined in a different way, so using some connection. So it's Finsler curvature coincides with the Riemannian curvature coming from this Riemannian structure GB. So this is a very useful characterization. And here, this vector field coming from the initial direction. So we start from a different direction, then we have a different Riemannian structure. So the curvature in this direction is not related to the curvature in this direction. So this characterization is useful only in this direction. But anyway, so this is very nice characterization. And actually, there are some almost immediate consequences like the Bornemeier's theorem. And actually, even for a curvature dimension condition, but by this characterization, it's very, yeah, it's very convincing we have the curvature dimension condition in the Finsler case. So since the optimal transport is done by geodesics, then yes, here is, yeah, as a vector field, we may consider a vector field coming from optimal transport, and by this characterization, it's natural to expect the curvature dimension condition holds in the Finsler case. So this is about Finsler curvature. Okay, then how about measure? So this is another difference between Riemannian and Finsler. Yes. So in the Riemannian case, we have canonical volume measure, and for arbitrary measure, we decompose it by using the volume measure. But in the Finsler case, we don't have a canonical measure in a sense. I mean, we can mimic the construction of the volume measure in some ways, but then we have different measures in general Finsler case. So in the Riemann case, they do coincide with the volume measure, but in the Finsler case, there are several ways, and we don't have a unique measure. So this is difficult in the Finsler case. And then what I did is that instead of choosing some measure, we start from just arbitrary measure. Then so we modify the construction of the weighted Bakurian-Ricci curvature in the Riemannian case, and so we can define the weighted Bakurian-Ricci curvature also in this Finsler case. So a Finsler manifold with arbitrary measure. So this is weighted Ricci in the Finsler case. And then, so let me explain a bit more about the definition of this measure. Okay, so we fix, as I said, arbitrary smooth measure on the manifold. And actually we can, here we explain by using the Riemannian characterization, as I said. So we, for a given non-zero tangent vector, we can consider a vector field V as in the characterization. So this is an extension of this vector to a vector field on a neighborhood of X, and every integral curve of V is geometric. Yeah, for the Finsler metric, but it's also geometric for the metric GB. Then we decompose our measure by using the volume measure coming from this Riemann structure, induced from vector field E, like this. And also we let Gan be the geometric with initial vector V. And now with these notions, the weighted Ricci curvature, but the Ricci curvature is now defined just in the Riemannian case. So I just recall the now very famous definition. So and here I remark that we also consider non-positive value here for capital N. Okay, so for the channel defined like this, so this is the usual Finsler curvature. And here is the effect coming from the choice of measure. And also reach infinity and reach small n, I defined as the limits. So this is which curvature, and we are always interested in the situation that the Ricci curvature is bounded from below. More precisely, Ricci n is bounded from below by k, in the case some real number. And this more precisely means that Ricci n of V is bounded from below by k times f square of V for any tangent vector. And so we can extend reduce machinery in the Riemannian case to this Finsler setting. So first of all, as I said, we can show the curvature dimension condition. Actually, the CDKN is equivalent to this curvature bound. And actually, this motivated the introduction of the Riemannian curvature dimension condition. Since I think, so this is, in a sense, on the one hand, a good news, since the curvature dimension is very powerful, and it is very nice to have this technique also in the Finsler case. This is very nice. But on the other hand, this means that if we are interested in some real Riemannian property, like isometric splitting theorem, then so CD it is not good enough since we include Finsler. Okay. So we need to put some Riemannian condition plus CD condition, and it is a Riemannian curvature dimension condition. So introduced by Nicolai and Ambrosio Gigli, Savare, Elba Quadrascio. Yeah. And actually we can show isometric splitting by using Riemannian curvature dimension. And also localization, or of course needle decomposition is very useful, interesting technique. It also extends to the Finsler case, and also the gamma calculus. This is very successful theory in analysis and probability by Buckley and his collaborators, and we can also extend this to the Finsler case. And in the gamma calculus, the most important ingredient is the Bochner inequality, and in the Finsler case, the Laplacian is non-linear, but we can somehow modify the Bochner inequality into the Finsler case. It's one done by Mathias Braun too. And then we can develop some kind of nonlinear analog to the gamma calculus in the Finsler case. Okay. And so now in the Lorentzian case, we already have cavity dimension constraint localization, as we explained in the ESI talk. And so now it's natural to consider Lorentzian counterpart to the CD in the Finsler spacetime. Okay, and following the Lorentzian case by Robert Marquand, Montin-Sur, and Charles Montin, so everyone is here, I think. Okay, so this is the motivation of our joint work. Okay, so now I turn to the Lorentzian. Okay. So let me emphasize our standpoint. So the Lorentzian case is, of course, classical, very well studied, and weighted Lorentzian manifolds were rather recently studied by Jeffrey Case and Galloway, Ulga, Wiley, and they show some splitting and singularity theorem. Yeah. Okay, so if the metric is reversible, we can define the Hausdorff measure, and actually it's called Boltzmann-Hausdorff measure, but in some research, Boltzmann-Hausdorff is not good. Some other measure is good. So this, yeah. Okay, so weighted Lorentz was studied more than 10 years ago, and also there are Lorentz-Finsler manifolds, and we for the definition of beam, and also Ettore wrote many nice papers about in this setting. And also we consider weighted version of Lorentz-Finsler manifold. And also, as in the talks yesterday, these are already nice synthetic approaches. Okay, so let me give the definition of Lorentz-Finsler manifold for completeness. So we again consider just smooth manifold, and then the Lorentz-Finsler structure is a function L on the tangent band, which is again smooth away from the zero section. And we have the positive homogeneity, and in here we indicate it just by as second order homogeneity. And instead of a strong convexity, we assume that this Hessian has the Lorentzian signature. In our case, we choose this signature minus plus plus plus. Okay, so in this case, again, we assume only the positive homogeneity. And actually, this homogeneity turns out more natural, even more natural in the Lorentz-Finsler case, since we will deal only with future direction. So we don't care about past direction. Then, yeah, reversibility that does not play any work. So non-reversibility seems natural in this setting. Okay, then similarly, okay, then so to make it space-time, we need a time orientation. So It's just as usual, we assume that there's a smooth vector field, which is always time-like. Then we call this Lorentz-Finsler structure, time-oriented by this kind of tangent vector field at Finsler space-time. And the future cone will be denoted by omega x. And as usual, all curves are time future directed in this talk. And yeah, so this is again summary of usual construction. So we can define a length, a kind of length for causal curve, gamma. And here, f denotes this, the square root of minus 2 times L. Okay. Then we can show we can introduce the distance over the time separation function, just as usual. And by using the time separation function, we can discuss what is geodesic in this context, and we can also write down geodesic equation. And by using geodesic equation, we can introduce Jacobi fields. And by Jacobi fields, we can introduce curvature. Yeah, so we can also follow this standard line in the Lorentz-Finsler case. And also I remark that we again have Lorentzian characterization of Lorentz-Finsler curvature by using this approximating Lorentzian structure. So this is same as the Riemannian characterization in the positive definite case. And so this is a bit a digression, but let me remark that the triangle comparison rules out to Lorentz-Finsler structures. So this is similar to the well-known fact that the Baraha space is a Cat0 or Alexander curvature bounded from 0 by 0, if and only if it's a Hilbert space. And actually, it's very easy to show this. So I can explain here. So yeah, so we have a curvature band from below or above by some constant on a Finsler manifold. Then by scaling argument, we see that the tangent space has non-positive or non-negative curvature. Okay, so if we consider Finsler manifold, whose curvature is bounded from below by K or bound below or above by K, and I mean in the sense of triangle comparison. And by scaling, we show that tangent space has curvature bounded from below by or above by 0. So Cat0 or Alexander non-negative curvature in terms of triangle comparison. And so we are in the Baraha space settings, and you see that if we consider just two vectors, V and W, and say the Cat0 condition means that we consider the midpoint of V and W, then we consider these triangles, and the Cat0 condition is just maybe B minus W or W minus B. But anyway, so this is the Cat0 condition for this triangle. And then, so due to the linear structure of the tangent space, we can consider a different triangle, like, this triangle. Then we have the opposite inequality. Okay, So in the first case, we have the upper bound of this this plus this by this plus this. Then we have opposite inequality for this triangle. Upper bound of this term, this plus this by using this plus this. This opposite inequality. And we have its equality. And equality is the parallelogram identity, so it's necessary a Hilbert space. This is very well-known argument in the positive definite case. And we can mimic this discussion in the Lorentz-Finsler case, and you can easily see that if a Lorentz-Finsler manifold, Finsler space-time has time-like curvature bounded below or above by some constant in the sense of triangle comparison, then it necessarily satisfies this. So this approximate in Lorentzian metric actually coincides with L. And this means that L is always written like this for all P. So this means that L is necessary in quadratic. And so it means that triangle comparison rules out Lorentz-Finsler. Okay, so this is just a remark about the difference between Lorentzian and Lorentz-Finsler. Okay. And so, okay, in the Lorentz-Finsler setting, we again consider weighted Ricci curvature. So we fix some smooth measure on this space-time, and as in the positive definite case, we start from some, in this case, time-like vector, and we extend it to a smooth time-like vector field. And we can obtain the Lorentzian metric coming from this vector field. And we decompose our measure by using the volume canonical measure associated with this Lorentzian metric. And then we define the weighted Ricci curvature just in the same way as the Riemannian or Finsler case. Okay, so this. Then, so I want to give one remark about the role of the real parameter capital N. So just by definition here, so this is the only part this capital N appears. And then just by looking at this term, we see that so Ricci N of P is non-increasing in this parameter N in this range between the dimension small n to the infinity and also minus infinity to 0. And more precisely, so we have this monotonicity. So each small n is the smallest curvature. And from small n to infinity, it's non-decreasing. And so Ricci infinity is also interpreted as Ricci minus infinity. And it's again non-decreasing from minus infinity to, say, 0. So, and as I said, we are interested in the situation that this curvature is bounded from below by some constant. And then by this monotonicity, we find that, for example, Ricci 0, the lower bound of Ricci 0 is weak, actually much weaker than the lower bound of Ricci infinity. Okay. So this is immediate consequence of this definition. And then, so by using this weighted Ricci curvature, we can write down the weighted version of Ricci-Hurdy equation and also associated Ricci-Hurdy inequality under suitable Ricci curvature bound. And let me explain about them briefly. So, okay, so I don't explain every notations. So if you know Ricci-Hurdy, it's you can see what this means. So, yeah, just as in the usual, I think, Lorentzian case, we consider a non-singular Lagrangian subfield and define these kind of quantities. Then we have we first have this Ricci equation for Lorentz-Finsler, I mean, no unweighted case. So this is by me, by Ettore. And then we modify these quantities into the weighted case. And actually, it's done like this. So we, again, decompose the measure like this. And by using this weight function, C, we modify these quantities like this. And actually, sigma is the same. Actually, we can define the sigma depending on the measure, but actually it coincides with the unweighted sigma. Then we just modify this equation by using these weighted quantities, and we arrive at this one. Yeah, this is very similar, but here we have a capital N instead of a small n. And here we have Ricci instead of the usual Ricci curvature. And then we have this additional term. And then the point is when this coefficient is non-positive, non-negative. And actually, by using this capital N minus 1 times capital N minus small n, you see that this coefficient is non-negative in our range. And actually, we can extend a bit to 1. Yeah. So in this range, we consider this coefficient is non-negative. And so this is good enough to show associated weighted Ricci inequality and Ricci curvature band. And we have some singularity theorems and comparison theorems, and also a kind of splitting, but this is very, very weak splitting theorem. In the Finsler case, we don't have an isometric splitting. So we can just say that there's a one parameter family of isometries by translations. So this is the most we can expect. And actually, we need to put very strong assumptions to show this splitting. So we're not very satisfied, but anyway, we have very weak but still non-trivial splitting theorem in this context. And also we can also generalize by introducing a notion of epsilon range, but it's beyond the M of this talk, so I don't explain. But anyway, we can show this kind of standard applications in the Lorentzian case to this weighted Lorentzian, weighted Finsler case. Okay, then finally I will explain a bit about the time-like curvature dimension condition. Okay, so I don't explain anything about time-like curvature dimension condition, so you already studied it yesterday, so I just say that in this context we can also show the time-like curvature dimension condition. So we consider just the global hyperbolic weighted Finsler spacetime, then the weighted Ricci curvature band, Riccian band from pi k, implies time-like curvature dimension condition, TCDQK, for any real number k and also any in this range. Okay, so there are some remarks and some remarks. So it turns out the weighted Ricci inequality I explained is good enough to show this TCD condition, and for expert, then let me emphasize that this is enough to show the original version instead of the reduced one or the entropic one. Okay, so this is because that the Ricci equation already is about after decomposition of the motion and the perpendicular direction. So the weighted Ricci equation is only for the perpendicular direction. So then it's natural to have the original TC condition. And also we include this non-positive dimensional parameter. So this case, actually this case, the proof is very same. So yeah, there's nothing new, but at least it's not included in previous papers. And also we can also show the converse as usual from TCD to the Ricci curvature. So this is the now joint work in progress in Braun. Okay, then having a bit more idea about this non-positive range, let me also explain the Riemann-Koski inequality. So the Riemann-Koski inequality is a standard application of curvature dimension condition. So, and in the time lag case, we can also show this. So we concept two compact sets A0, A1. They are causally related like this. And then the T of A0, A1 is the set of intermediate points. Then we have this Riemann-Koski inequality for under non-negative rich n, and n is negative. So this seems very much like the classical Riemann-Koski inequality in the Euclidean. Yes, but because this n is negative, we have opposite inequality. Yeah, so since this is negative, we have opposite inequality naturally. And in the limit case of reach 0, we have this very degenerate concavity of this measure. So more precisely, the Kasai concavity of measure. Yeah, we have this kind of Riemann-Koski inequality under this curvature condition. Okay, and finally, there are some first questions. So one natural direction everyone can have in mind is, of course, this analog of Riemannian curvature dimension condition. So there, as I said, in the Finsler case, we have curvature dimension condition in the Finsler manifold, and then we need to introduce some Riemannian version of the curvature dimension condition. And also in the time-lag curvature dimension condition, we have a similar story. So as we showed for the Finsler spacetime, we still have the time-lag curvature dimension condition. Then if we want to show some splitting theorem, asymmetric splitting theorem, then we need to introduce some Lorentzian condition, say Lorentzian time-lag curvature dimension condition. Yeah, so this is, I think, a natural direction, and I think in the next workshop, someone can talk about this. I think so. and also, this is a naive question. I'm not sure this is natural from the Lorentzian point of view, but the gamma calculus is, as I said, very powerful, successful theory in the analysis and probability. And yeah, if it has some applications in the Lorentzian case, I think it's also nice. And also Lorentz-Finsler case, we of course need to consider non-linear analog of this concept. And okay, so I stop here and thank you for watching. So there are some references.